Hello to my virtual audience. I'm Saharon Rosset from Tel Aviv University. This is joint work with Ruth Heller, Amichai Pensky, and Huda Aroni. And I'm going to be talking about optimal and maximin procedures for multiple testing problems. So if we think about sort of classical approaches for multiple testing, we have at the top, let's just start by thinking about the simplest multiple testing setup of having two hypotheses and wanting to control the family-wise error rate. Then at the top, we have some methods, some classical methods or some commonly used methods. We could use Bonferroni-Holm, or maybe we could also use CDAC, but for our purpose, let's just talk about Bonferroni-Holm, or we could use Stuffer's method with closed testing. It doesn't really matter for if someone doesn't know what it is, but let's just make sure we understand what we see in the plots here, because that's the kind of our way of presenting multiple testing procedures that is going to play out throughout the talk. So we are considering here two hypotheses. So we have two p-values, U1 and U2. And the Bonferroni-Holm and other methods we're going to consider are symmetric in the sense that if we transpose U1 and U2, we also transpose the rejection decisions. So we only show what happens when U1 is smaller than U2, so under this diagonal line. And in red, we have the region where we reject both hypotheses, and in blue, we have the rejection where we have the region where we reject only the smaller p-values. So this is what Bonferroni-Holm looks like in that sort of way of displaying it. And what we're going to be doing throughout this talk is we're going to be generating rejection regions that for this problem would look like this. And we're going to be doing that by asking ourselves what's the best, optimal, most powerful method that we can design for solving these problems. So really, what we're going to, at least the first part of my talk, we're going to end up with a description of how we get these rejection regions for the same problems, Okay, so a quick refresher on hypothesis testing. So a hypothesis test is basically a competition between two distributions that we hypothesize for our data. So we say we have some data X, and under the null, it has some distribution F0. So a simple hypothesis test is a competition between two specific distributions under the null hypothesis and under the alternative. And we're going to be assuming throughout that these are distributions that have densities. And if the distributions have densities, that the Neyman-Pearson lemma tells us that the best possible, most powerful test is to reject for high values of the likelihood ratio, which is this ratio of the densities. So the optimal rejection region is to reject for high value of this likelihood ratio statistic. And we can reformulate this problem in terms of p-values, which is going to be convenient for us. So to reformulate it in terms of p-values, we simply transform X using the cumulative distribution of the likelihood ratio under the null. And this gives us that under the null, this transformation gives us a distribution, a random variable with the uniform 0-1 distribution. And under the alternative, we get some other distribution, but the important thing is that now this distribution is, the density is a decreasing function by the transformation we did. So now the Neyman-Pearson lemma tells us to simply reject for small values of U. So that justifies interpreting this as a p-value. Okay, so this is very classical. The way I want to be looking at this problem is maybe in a slightly different way, or maybe it's not different, but I want to remind ourselves that what we're really doing is we're solving an optimization problem. we could do it in the U representation, and then the domain is 0, 1, or we can do it in the X representation, and then the domain is whatever our data domain is. But on every point, on every possible outcome, we have to make a decision, 0 or 1, whether we reject the null or don't reject the null, and we seek the policy that maximizes this integral, which is the power, the integral according to the alternative distribution, subject to a constraint on the integral according to the null distribution, which after the transformation is just the uniform distribution. And the interesting, maybe slightly surprising thing is that this problem, which is infinite because we have a continuous set of points where we have to make decisions, and it's integer in the sense that we require integer decisions. It happens to have this very simple optimal solution that's suggested by the Neyman-Pearson lemma, and we can just think of it as maybe a continuous knapsack of looking at the ratio between the constraint and between the objective and the constraint, and at every point in our space, and putting into our rejection region the points with the high ratio, and doing that until we attain the constraint. So a supposedly very frightening looking optimization problem has a very simple solution, and therefore we have the Neyman-Pearson lemma that tells us what the optimal solution is. Once we move to multiple testing, we can think the same way. Instead of having one pair of hypotheses, we now have big K pairs of hypotheses, and big K is going to be the number of hypotheses throughout my talk. Each one of them, once we transform, say, to the p-value, has a uniform 0, 1 distribution under the null and some decreasing distribution under the alternative. For now, we assume it's all simple hypotheses and all the alternatives are the same. And we're also going to assume that these p-values or the test statistics that they are derived from are independent, although in the paper we do deal with exchangeable dependence. So still a symmetric relationship, but with dependence. And as in the single test Neyman-Pearson case, what we really want to do, or what we argue that we want to do, is we want to design good tests. And what are good tests? They need to have high power. We have to define exactly what power means, and they need to control type 1 error in some sense to be valid procedures, valid tests. Okay, so this is basically our task, is to design good tests as good as we can, optimal if we can, for this problem in analogy to the Neyman-Pearson situation. So we're going to be using H to designate the true state of the hypothesis. So H is going to be a binary vector of length big K with each coordinate equal 1 if the alternative holds for the corresponding hypothesis test, and 0 if the null holds. D is going to be, we've seen that already, D is going to be our notation for a decision function, which is the function that gets a vector of statistics or a vector of p-values and decides which one gets rejected. So we reject the kth null if dk is 1. And notice that dk accepts the entire vector as input. So it's allowed to consider all coordinates in making its decision. R and V are the standard definitions in the literature. R is the total number of rejections, and V is the number of type 1 errors, not correct nulls rejected. And these are random variables that depend on the random vector of statistics that they get. And this D emphasizes that it actually depends on the policy we employ in making rejections. And because our problem is symmetric, we're only going to be considering a symmetric D function. So if we do a permutation on the p-values, we apply the same permutation to the decisions. And in fact, we can prove under some pretty mild conditions that every optimal policy would have this form. So it's really not an assumption. Okay, so now we have to define what we mean by power and type 1 error for multiple testing. So for type 1 error, we just employ the most, at least in this talk, we limit ourselves to the most standard definitions, to family-wise error rate, which is in the previous slide's notation, the probability that V is bigger than 0, or we can write it as the probability that this inner product of the world state times the decisions is bigger than 0, and the false discovery rate, which is the expected value of false discoveries to total discoveries. If we employ the conventions of 0 over 0 equals 0, then we can just write it like that. Otherwise, we have to account for the case of 0 discoveries. And I assume this family-wise error rate and FDR definitions are well known. But what we have also to define for our framework is a notion of power for multiple testing, because this is going to be what we will want to optimize, maximize. So here in this talk, I'm going to be considering these definitions. The first one is the average power for else false null. So it's the expected number of true rejections when L of the nulls, L smaller or equal than K, L of the nulls are false. And what we call minimal power for all nulls being false, which is the probability that if all nulls are false, I make any discovery. But really, this is pi L is going to be the focus of my presentation in this talk, at least. But the point is going to be that we can solve for either one of these, or for convex combinations of functions like this, and so on. So now we've defined several candidates for the power we're interested in optimizing, and we've defined the two candidates for the type of type 1 error control that we are looking for. And with any one of these choices, we end up with this generic formulation for our optimization problem. We want to maximize our selected power objective, subject to controlling our selected type 1 error measure for every possible vector H, for every possible world state, right? Because we are looking for strong control, so we need to control it under every possible combination of true and false nulls. So that would, in principle, give us 2 to the k constraints here. We actually have only k constraints because of the symmetry in our problem, the symmetry in our functions, and the symmetry in our decision. So we can limit ourselves to k constraints. But that being said, we are still very far from solving this, because we actually have this continuum of variables, or continuous domain, that we need to define the function d over. We need to get an integer solution. And what is worse, the problem is not even linear in D, because the family-wise error rate and FDR are not linear functionals of D, right? The family-wise error rate is an indicator, and the FDR is an expectation of a ratio of linear functions in D. So really, we seem to be very far from being able to solve this problem and get a Neyman-Pearson analogy for multiple testing. So the first result that allows us to make some progress is a very simple and intuitive result. And it says that the solution is what we call a weakly monotone, which is to say that the optimal policy, so this star would be the solution we are searching for our optimization problem, that this star is always going to reject a subset of the smallest p-values. So if the p-value ui is smaller than the p-value j, it's impossible that the optimal policy would reject the jth coordinate and not reject the ith coordinate. And that's kind of obvious and sensible, but it's not trivial to prove. But once we prove it, then actually it allows us to linearize all our functionals. And I'm actually not going to dwell on how exactly that happens. But yeah, it's in the paper, and I won't talk a lot about it. But once we know that we are only rejecting the the smallest p-values, then one thing we can do is limit our attention to that corner or octant of the space where the p-values are increasing. So the first one is smaller than the second one, and so on. And basically solve our optimization problem only on this set, because by symmetry, once I know what the optimal solution looks like on this set, I can, by reflection, have the optimal solution on my entire hypercube. So once I limit myself to this set of increasing p-values, that allows me to linearize my power objectives and my constraint. For example, for the family-wise error rate, if I know that I'm rejecting the smallest p-values, then for every state of the world, for every vector h, I just have to ask whether I reject the smallest p-value that corresponds to a 0 coordinate in h. And that basically can be reflected as a linear function on the Ds. So the point is that this allows me to write all of this as a very hard infinite dimensional integer, but linear problem in my Ds. So now I have this problem. The next thing I do, which I skipped over here, is I change my problem from being integer. I relax it to consider the continuous optimization problem. So where the Ds are allowed to be between 0 and 1 rather than required to be either 0 or 1. And with that, I have an infinite optimization problem. So for finite optimization problem, I have a well-defined, for finite convex optimization, in particular linear optimization problems, I have a well-defined theory of optimality by the Lagrange theory and looking at the KKT, Karush-Kuhn-Tucker conditions. For the infinite dimensional case, we have the Euler-Lagrange theory, sort of the functional analysis view on optimality. And it's actually designed to solve, to characterize what the solutions to substantially more complex problems look like. When we apply to this infinite dimensional, to this infinite linear program, what we get is a set of conditions that look very much like the KKT conditions for the finite case. And I'm going to show them, but not really dwell on them. But the important point is that the important difference is that for the infinite case, these conditions are not necessary and sufficient, as in the finite case, they are only necessary. So this is a view of what the optimality conditions look like when we present them in the same way that we're used to looking at the KKT conditions. And I'm not going to give any details. The important thing is that in terms of Lagrange multipliers, in terms of constraints in my problem, I have a finite set of integral constraints, right? These are the type 1 error constraints, and each one of them has a Lagrange multiplier. So these are just K constraints with K Lagrange multipliers. Plus, I have an infinite set of Lagrange multipliers associated with the complementary set, or associated with the inequalities on the Ds, the requirement that the D be non-decreasing. So that would be a continuum of these variables and the Lagrange multipliers. So this is sort of the structure that I can see in the problem. And then we have two additional results that quite surprisingly tell us that in some sense we can actually solve this problem. So the first one is saying that basically assuming all densities we're interested in exist and are defined on the entire range, then a solution that complies with this entire set of conditions is going to be integer, or it's going to be integer almost everywhere on our cube. So some of you may be familiar with the concept of total unimodularity for linear programming, for finite linear programming, that tells us that a linear program with total unimodularity structure is guaranteed to have an integer solution. So what we show here, or what we derive here, is basically some kind of total unimodularity for the infinite problem. So we have necessary conditions, and we know that any solution that complies with them is going to be integer. So in fact, the relaxation to the linear, to the continuous program has no effect. We are going to get a solution. If we can get a solution, it's going to be integer. The other sort of surprising result is that for this problem, we can prove that these necessary conditions are in fact also sufficient, in the sense that the solution that complies with them is going to be optimal for the problem. And it's basically based on writing down the dual to this problem and proving that the solution of these conditions will have zero duality gap. Meaning also in this case, it's in fact behaves exactly like KKT conditions, which are necessary and sufficient. Okay, so putting all of our results together, we have a theoretical result. It's not yet a practical result. It says if we choose power objectives that I mentioned and many others, and if we want to control family-wise error rate or FDR as well as many others, the optimal solution, the optimal procedure, the optimal multiple testing procedure can be explicitly found if we can find a solution that is integer, that complies with these KKT-like conditions, and that is feasible for the original problem. And with that, we can actually, and next I'm going to show how we can use that, or not really show, but tell you how we can use that to devise an algorithm to actually find the optimal solution. And now the key to designing an algorithm is this observation. The observation is, remember, we have these K-Lagrange multipliers associated with the integral constraints, which we denoted by mu. And the observation is that if I'm given a set of those Lagrange multipliers from somewhere, then that allows me to infer what D is. In what sense? In the sense that given the mu's, I can basically infer all the lambdas and infer D. This is like a closed problem. So that means that I can basically reduce my problem to the problem of finding a set of these Lagrange multipliers that give me a feasible solution. Once I derive this D of mu, if I get a feasible solution, then it is also optimal. So this actually gives rise to an algorithm, or it tells me what I need to devise an algorithm. I need some heuristic or other approach for searching the space of possible Lagrange multipliers, a k-dimensional space, not a high-dimensional space. Given mu, I need an approach I need to derive the D's. This is a closed problem, but I need to calculate these coefficients A and B in my generic optimization problem that I showed you. And then I need an approach to integrate exactly, but in most cases I cannot integrate exactly, so I need to do numerical integration to calculate these constraints. Okay, so and I need to do that because I'm looking for a feasible solution. I'm looking for a d mu that is feasible, and then I know that it's optimal. So the point of this part is that this is conceptually maybe a little complicated and computationally demanding, but it's possible to do this. And if we can do this, we can find optimal policies for multiple testing problems. So I'm going to demonstrate this by looking at controlling family-wise error rate and FDR for 3 hypotheses for BK equal 3 for testing normal means. So the distributions I'm interested in are these normals with variance 1, and the expectation is 0 under the null and some value smaller than 0 under the alternative. and I want to strongly control family-wise error rate and maximize, in these examples, just pi3. So pi3 is the expected number of true discoveries when all nulls are false. And what I'm going to be comparing to is the simplest and sort of most well-known solution for this is to Bonferroni-Holm. And so since I have three hypotheses, I have to explain how I show the resulting rejection regions. So now I have not two, but three hypotheses. And what I'm showing here are slices of the three-dimensional 0, 1 cube. And these are slices. My slices are limited to U1 is smaller than U2 is smaller than U3. So this is when U1 is equal this small value, what my rejection region looks like as a function of U2 and U3. And this is when U1 is equal to this value, which is 0.05 divided by 3, how my rejection region looks like. In green, I have the region where I reject all three hypotheses. In red, I reject the smaller two p-values, and in blue, I reject only the smallest p-value. And the slice I show here is 0.05 divided by 3, because for any value bigger than this, Bonferroni obviously makes no rejection. So we see, and the other thing we should note is that because U1 is the smallest, we have a white region here at the bottom, because this entire two-dimensional plot is limited to U2 and U3 bigger than U1. Okay, so this is what the classical Bonferroni-Holm solution for this problem looks like. And here we see the optimal solutions from our procedure. Now, it's not surprising to see that the optimal solution depends on the value of the alternative we are interested in. So here we have an alternative that is low power, close to 0, and here we have an alternative which is decent power. We can start by looking at this alternative at I equal -2. And what we see are rejection regions that are maybe not that different from Bonferroni. Qualitatively, these two are the same as we saw in the previous slide, but we see that something very interesting, that at smallest p-value 0.044, so almost at the nominal level, we still reject when the other two p-values are also small. And at this value, 0.05, so higher than the nominal level, the nominal level at which I want to control family-wise error, there's a tiny green point here. So if all three p-values are 0.054, I still reject all three of them in the optimal policy. So this is what it would look like at high power. At low power, I have, for example, at this value, I still actually have a substantial probability of rejection. And one thing we should keep in mind is that under this sort of this low power alternative, so that means that somehow tiny p-values are not really maybe that consistent with the alternative, but these sort of small but not tiny p-values are actually quite consistent with the alternative, and that could be an intuitive explanation why we get these kind of rejection regions looking this way. Next, we're going to look at the same thing for false discovery rate. And for false discovery rate, the gold standard is Benjamini-Hochberg. I'm showing here what's called minimally adaptive BH. It's a paper by Solari and Gomen. And so this is the sort of the well-known Benjamini-Hochberg rejection regions. We see that minimally adaptive BH would still make rejections when all three p-values are around this 0.04 value. So here there's again a tiny green dot. This is what the optimal solutions look like. And to get to other things, I'm not really going to dwell on this too much. But this phenomenon at the top is a phenomenon that some of the audience may be familiar with, is the idea that in very low power situations, the optimal thing that we can do for making rejections with FDR control is either reject all hypotheses or reject none. So we have a proof in the paper that for some range of weak alternatives, low power settings, the optimal policy for FDR control is either to reject all hypotheses or reject none. When we move to the more powerful alternatives, we get behaviors that are still distinct from what BH does, but maybe not so drastically different. But we can still reject when all three p-values are 0.1, we still reject all three of them at this alternative. Okay, so I've shown you the rejection regions. Here is what we get in terms of power increase. So we compare under our selected objective, which is pi3, we compare the power of, for family-wise zero, under family-wise zero rate control, the power of Monferroni-Hahn to the power of our optimal multiple testing policy. So we see we get more than twice the power or the expected number of rejections in this low power setting, and about 20% in the high power setting, higher power setting. And similar picture for FDR, we actually get higher increase in power. We see at the bottom of the FDR table, we get higher increase in power from moving from BH or minimally adaptive BH to the optimal policy. Okay, so what we've shown is that we can, in principle, find optimal procedures for strong FDR or family-wise zero control with simple alternatives. The computations are hard. I haven't shown you, but I've indicated that they are hard, and indeed, we do it up to 3 hypotheses currently. So if we want to get this to be maybe more interesting or more practically useful, there's 2 things we have to primarily be concerned with. First one is obviously going beyond simple tests to considering complex, at least alternatives, because in scientific hypothesis testing, it's very rare that simple alternatives are appropriate, and complex alternatives, complex one-sided alternatives are more appropriate. And of course, we need to worry about dealing with larger K, either design approximations or actually look at problem formulations that allow us to do large K. So what I'm going to be talking about today is dealing with complex alternatives under strong control. And in Ruth Heller's talk, she's going to be touching on solving high-dimensional problems by moving from strong control to the 2-group model. Okay. So what do we mean by maximin? By maximin, we mean that instead of assuming that we have a simple null and simple alternative as before, we actually have a one-sided alternative. So in particular, we want our error control. We want to have strong control so strong control means for all possible vectors H, for all word situations, but also for all possible vectors theta, for theta being a k-dimensional vector of parameters that are sort of a one-sided alternative for the null. So we've formulated a much more demanding set of constraints here that says we don't want to control only for a given set of parameters, we want to control for all possible parameters. And remember that in multiple testing, the control criteria depends on the value of the alternative. And in the objective, we also have a range of values of the parameter that we are interested in. The only thing is we need to choose what we optimize. So we say we want to maximize the minimal power among all alternatives of interest. And in fact, we could allow the alternatives to be different in the objective as well. But we are going to limit them to some subset of the one-sided alternative. And we need it to be a strict subset because or we need it to be bounded away from 0, from the null, because as we get close to the null, we know that the power decreases to the level, and it's uninteresting. So we say, we define a set of interesting alternatives for the power and all possible alternatives for the level. And I'm going to skip the details which are a little involved, but the point is that we have a theorem which is a sufficient condition, which is a recipe that if you can find some type of solution, then you know that it's actually a solution to your minimax problem. Sorry, and the point is you have to find basically two values: a value in the alternatives you consider for the power, and a value in the entire set of alternatives you consider for the control, for the error. And if you can find an optimal solution for what we call a single objective problem, which I haven't really defined, and you can show that it complies with some condition over the power, then you found an optimal solution for the maximum problem. This is a sufficient condition in the sense that we don't know where it holds, but if we are able to find it, we can confirm optimality. And in our experiments with the normal means problem, we've been able to find these and confirm the optimality. So this is what the maximin optimal solutions look like for our problems. So here I'm going to show you for two hypotheses and family-wise error rate control. At the top, we have what we actually saw in the first slide is the simple tests optimal solution. At the bottom is the maximin solution. And here at the top, this is theta equal 0.-5 on the left is the value of the alternative we are considering. And at the bottom left, it's the highest point in theta b. So theta b is from, in this case, from -0.5 to -infinity. And we see the difference in rejection regions we get from the simple solution to the maximin optimal solution. And in particular, we get some interesting and curious phenomena, such as that white hole that's in the middle of the circle. So that white hole below the red, which is maybe a little hard to see, says that we have some point in the red where we reject both hypotheses. We go down and left, meaning we decrease both of the p-values, we improve both of the p-values, and we reach this white region where we reject none. Okay, so some might say it's absurd behavior, some might say it's interesting behavior. And once we consider that the alternative, that the power objective deals with very low power alternatives, whereas the error constraint deals with higher power alternatives, ends up dealing with higher power alternatives, that actually can explain this in terms of thinking about things like likelihood ratios. But I won't go into the reasons for lack of time, but I point out that we get some interesting, strange behaviors, but I emphasize that these are the maximum optimal solutions for these problems. As we make the problem more powerful, as we are interested only in more powerful alternatives, as we move, say, to the right column, we get that the maximum region at the bottom is starting to look actually quite similar to the simple test at the same alternative. Okay. So just to show that this gives us something, what this shows, what this table shows, is the power we attain from the single alternative formulation, which we call OMT, and from the maximum formulation for family-wise error rate on the left, for FDR on the right. So, for example, at this -0.5, we see that by moving from the simple optimal to the maximum, we do lose quite a lot of power. At -2, the last row, we lose very little power. And this is consistent with the fact that the rejection regions look quite similar. But still, everything is obviously more powerful than the existing alternatives because it's guaranteed to be more powerful. Okay, I'm going to skip the case study for time constraints. Once we move to dealing with real data, it gets more complicated, but we are able to demonstrate the advantage also for real data in pretty convincing ways of adopting these optimal policies as compared to the standard policies. So the last thing I want to talk about is this strange behavior of getting what we call non-monotone rejection regions. So anytime in our rejection regions, anytime we have a slope that is positive, even if we don't have a hole like on the bottom left, if we have a slope that is positive, it means that by improving our p-values, we actually decrease our rejections. So any positive slope is actually, in some sense, counterintuitive. And one important question that I think has a clear answer is whether this is a property of the solution we find, or is it a property of the problem? So it's very clear that this is a property of the problem, and in particular, it's a property of family-wise error rate and FDR as the criteria for error we are controlling. So in my view, in our view, this actually exposes properties of the problem formulation that we might be interested in thinking about more deeply, in trying to understand what's the right problem formulation. However, one thing we asked ourselves is, can we impose sensible behavior in additional to optimality? So require the optimal policy subject to also not violating this condition that when the p-values improve, their rejections must not deteriorate. So the point was to add an additional set of constraints, what we call weak monotonicity constraints. And this makes the problem substantially more complicated and more computationally intensive, but we can still solve it. We can think of it as adding kind of an isotonic regression on top of the Lagrange multiplier search. Obviously, I won't go into details, but I'll show you the result of doing this. So on the left, we have solutions that we've already seen. This is at the top is the maximin for family-wise error rate control that we've seen. This would be the middle column in the maximin plot I showed you, the middle bottom. And this is what happens when we force monotonicity on this solution. So we also require this monotonicity. In the bottom left is something we haven't seen, is the FDR actually for simple hypothesis also violates, has a positive slope. And on the right bottom is what happens when we enforce monotonicity. And this also says that we lose a little bit of power of our power objective when we move from left to right on the top row, not very much, a few percent. And we lose very little power when we move from left to right in the bottom row. But we can also basically solve our problem subject to the additional requirement. Okay, so to wrap up with a brief discussion, specifically of the computational issues. So in these demonstrations, we solved problems with up to 3 hypotheses. We are working and will expect to soon have approaches that can solve pretty accurately up to 10 dimensions, but not sure at all that we can go to 100, and we do not expect that our approach is as presented here is likely to be appropriate for thousands of hypotheses, which is of course important in modern scientific domains like genetics, physics, and so on. And Ruth Heller's talk, which is I think supposed to follow mine, is actually going to show how within the 2-group model for large-scale testing, we can apply sort of somewhat related thinking about optimality and solve the problems for thousands of hypotheses. But this is going to be in her talk. So to summarize, we think it's self-evident that having high power is what we want from good tests. This is how we teach in Stats 101 Neyman Pearson. And it seems clear that this becomes more critical and not less critical as we move to multiple testing. So this gives us this formulation of optimal multiple testing as optimization problems that are hard problems. What I demonstrated is that in principle, it can be solved and give these novel and more powerful procedures, but there are substantial computational and theoretical challenges, and the maximin approach that I presented, plus maybe the addition of monotonicity and the two-group model that's going to be presented in Ruth Heller's talk, are two directions that to some extent overcome the challenges and produce practically useful tools. So thanks a lot. I hope there'll be questions and discussion, but it won't be now. Thank you.